When we think of probability, we usually don't think about geometry. We usually think about how many times will I get heads if I flip a coin, or how many times will I roll a 5 if I roll a number cube. But there is an application of probability in the world of geometry, and that's what this video is all about. Let's take an example, a checkerboard. Let's pretend that this checkerboard is going to be our dartboard. We want to figure what is the probability that if I throw a dart at this checkerboard that I will land on a white square. Well, we can look at what we have here. We can count up the number of squares, how many of those are white, and that can give us a good probability. In this case, there are 64 total squares. 32 of them are white. So the probability of a white square is 32 over 64, which is 1/2, or 50%. Now, looking at this situation, that makes perfect sense. But now let's look at it from a different perspective as opposed to just counting the squares, and see if that can help us understand how geometric probabilities are computed. Let's take the same checkerboard. Let's give some dimensions to each one of our squares. Let's pretend for a moment that each little square is 1 centimeter by 1 centimeter in size. So the area of each square would be 1 times 1, which is 1 centimeter squared. If we add up all the different areas, the total area of our checkerboard would then be 64 times that, because there's 64 squares, 64 cubic centimeters. And the area of our white squares is 32 squared centimeters. And interestingly enough, the ratio of those two areas, 32 over 64, still comes out to be 1/2. Let's take this situation, let's change our dimensions and see if that's just a coincidence that the ratio of those areas happen to be the same, or if it's something that'll hold true all the time. Let's take the same checkerboard. Now let's pretend that each square is 4 centimeters by 4 centimeters. So that means the area of each square is 4 centimeters times 4 centimeters, which gives us 16 centimeters squared. So our total area equals 64 times 16, because we have 64 squares, each one is 16 centimeters squared, and that gives us 1,024 squared centimeters. And the area of our white squares equals 32 times 16, which is 512. And if we check the ratio of those two areas, we find out that it still reduces to 1/2. Interesting. So let's take what we've seen now pictorially and turn that into a general principle. Based on what we've just seen with the checkerboard, we can now say that a geometric probability is the ratio of the area of the target region divided by the total area of the target. And if you think about what we know about probability, it's the number of outcomes that are true or desired over the total number of outcomes, then you can see how geometric probability fits into that same scenario. Tomorrow in class, we will use this idea, this concept, to see geometric probability at work with various shapes and sizes of targets and regions.